Hey guys, I didn't have time to post a video last Friday, so yeah, I'm taking you on a walk in spring Norway instead. So if you saw my video 2 weeks ago and believed it, I'm sad to say that was an April Fool's joke. We do not yet have the ability to travel through time or send information through time. However, it's not that insane, because the research I was talking about by the professor I was talking about is actually being done. But last I heard of it was in 2002 when he was starting the project, and I haven't heard anything yet, so I don't know. I'm guessing there won't be any results anytime soon anyways. Turning around. However, today we're going to talk about the 4 fundamental forces. They are, in order of magnitude, gravitation, the weak nuclear force, the electrostatic force, and the strong nuclear force. The strong nuclear force is responsible for the attraction of the particles within an atom, that is the neutron, the proton, and the electron. It also works on subatomic levels, but we won't be taking that today. The electrostatic force is responsible for the attraction between electrons, and it's why we can have such things as electricity and magnets. The weak nuclear force is mostly relevant when it comes to nuclear decay. Gravitation is of course the force we all know that if I drop you guys now, you will fall and crash to the ground, and I don't want that because you're expensive. And change hands. It is also why I now got tired in my hand from holding you so long. Now we also see gravitation as a really strong force, right? It's what holds the entire planet Earth in orbit around the sun, and it's responsible for most force we see around us. However, this is not true. Gravity is, as a matter of fact, the weakest of the forces, and they're all measured in relative measures, relative to either gravitation or strong force. So now we will do them in order of gravitation. Setting gravitation to 1, the weak nuclear force is 10 to the 25th time stronger. The electrostatic force, however, is 10 to the 36th time stronger, and the strong nuclear force is 10 to the 38th time stronger. Imagine the force when you drop, say, a kettle on the ground. That's quite a lot of force, right? However, the strong nuclear force is 10 to the 38th time stronger. Our gravity does have some upper hands, of course, because gravity is not limited by range and can therefore work over all distances. This means that I am affected by every other thing in the planet, the gravity. However, of course, the biggest mass close to me is the Earth, so that's what I noticed. The strong nuclear force is much stronger, as is the electrostatic force, but they both work on very small ranges. So they don't really affect us very much in day-to-day life. Now that's quite silly to say, because if we didn't have the strong nuclear force, we would simply dissolve and be nothing. But now, one of the big tasks physics has in front of it is creating what we call a theory of everything. It's supposed to be one theory that can explain everything in the world, and currently we do not have this. We have a theory of relativity that explains things in the big world, and a quantum theory that explains things in the small world. And then there's several gaps in those as well. One of the things that would be necessary if we were to actually make a theory of everything would be to make an equation that would combine all the forces into one. Currently we've done so for 3 out of the 4 fundamental forces. That's the strong nuclear force, the weak nuclear force, and the electrostatic force. However, we have not been able to include gravity. This is the big problem, because it means we don't have a functioning physics model that explains the universe. We can explain the things we see around ourselves, but they don't match up with the physics of quantum mechanics, which is the physics of very small things. And it will be very interesting to see what people make of this problem as time goes, and it's one of the big major problems we still have in physics. I'll include a link in the description to an article about the theory that gravity isn't really a force, however absurd that sounds. It's a very good article, but it's quite lengthy. That's all I have for you today, guys. Hopefully you liked spring Norway, even though it's just me walking up and down the road. See you next week.